Hi guys, you are in Teacher J channel, and for today's video we are going to discuss one topic in chemical reaction engineering, which is on stoichiometry for batch systems. So as you may know, when we design a chemical reactor, we are we should use design equations, and then it must be made sure that you have sufficient data regarding the rate of reaction as a function of conversion prior to using the appropriate design equation for the desired reactor. Unfortunately, most of the times, you don't have any data or any experimental data with respect to the reaction rate and the conversion. So you don't have any, sometimes or most of the time, you don't have any data for the design. However, um, despite the fact that we don't have any data, we can still create a mathematical relationship between the rate of reaction, okay, of a certain component as a function of conversion, assuming that you have with you or you know already the rate law of the chemical reaction involved in your design. So despite not having the correct data, or I mean the accurate data, because of some reasons that you may have encountered. So despite that fact, as long as you know the rate law and you know how to transform the rate law equation into a function that has conversion in it as the independent variable, then you will be able to design reactors according to the desired conversion, or better yet, according to the desired concentration. So it really depends on the situation. As long as you will be able to relate the given rate law to the appropriate stoichiometry of the chemical reaction, and then that's the time that you can start designing your reactor. So let's start analyzing first the stoichiometry for batch systems. It's very important to lay out or to organize first all the necessary stoichiometric equations with respect to a chemical reaction in the form given in the screen. So you have here A and B as the reactants and C and D as the products. And we let our A the limiting reactant. So of course, when we deal with chemical reactions, there must be or one or both or one or yeah, probably one or both should be the limiting reactant or the reactant that will be consumed first. So assuming that we let A the limiting reactant, and we assume or we let our calculations be with respect to A, so we can rewrite our chemical equation in this manner, wherein the stoichiometric coefficients for B, C, and D are with respect to A. So these are basically what we call the stoichiometric ratios for each of the reactants and the products that are with respect to A. So let's start first deriving the batch system stoichiometric equations, which will involve the variable n, or the number of moles. So the scenario for this one is that you initially place the components, probably the the starting point of the reaction probably may have only A or B first without C or D, or it may be that you captured the reaction wherein C and D are present together with A and B. So it depends on the situation. So of course, at time zero, we need to assign values for the number of moles for both the reactants and the products. So for A and B, which are the reactants, we assign them as Na0 and Nb0. For C and D, we also assign them as Nc0 and Nd0. So these are the variables for the initial number of moles for both the reactants and the products. All right. So as you can see here, we have here Ni0. So I here actually refers to the inerts, or the number of moles of those components that do not participate in the reaction but are present inside the reactor. So they must also be taken to, they should be taken into account, okay, as part of our balances, okay. So considering that the inerts do not participate before and after the chemical reaction, so you could also say that at time, or at a specified time or final time, the inerts at a final time or a specific time interval will be equal to its initial value, because it does not, or it is not consumed, or it's not generated along the process. So it is just the same. For A, B, C, and D at final time, or at a certain time value, so these are termed as Na, Nb, Nc, and Nd. So as you can see, they are devoid of the zero term, because the zero terms indicate that these values are initial. Okay, so recalling the concept of conversion. So of course, the conversion in this case will be based on the limiting reactant, or which is component A in this case. So recall that the equation for conversion, okay, x, or you can just write it as xa, because of course in the entire derivation we are going to depend everything on A, or we are going to base everything on A. Recall that xa is just basically the difference between the initial minus the final A. So this difference actually indicates the moles of A converted. Okay, and then this is over the initial value of A. All right. So now, if we are going to rewrite this and re-express this equation in terms of number of moles, so we can rewrite this in this manner. So we have here xa Na0 is equal to Na0 minus Na. Oops. So we can actually rewrite this term in a manner that on the right side, I mean on the left side, we can actually rewrite the Na, or the final number of moles of A, and then get the difference, okay, the between Na0 and Na0 times Xa. Okay, sometimes other textbooks write this one as like this only: Na equals Na0 minus Na0x. So regardless if it's xa or x, that is just the same value, and the x value would always depend on A, which is the limiting reactant. Okay, so this is the relationship between the final value of your Na and the initial value of your Na. So how they are related, okay, with respect to the term conversion, or with respect to the conversion term. So this term over here serves as our final value, and then this will be our initial value, and this will be our change value, or how much was consumed. Okay, so we call that change value. So as much as we are comfortable, or we find it easy to have this formula for component A, because this derivation is based solely on limiting reactant, so that will be the basis. However, we also need to know the stoichiometric equations for NB, for NC, and for ND as well. So how do we do that? Of course, we um, we are already familiar with the fact that the initial values of NB, okay, I think it would be better to, okay, so let's write it in this manner. So let's have the species. So we have here the A, the B, C, and D. And then we have here the, yeah, initial terms. And then we also need to know the change terms, or how much was consumed or how much was generated. Okay. So the initial values are, of course, NA0, NB0, NC0, and then ND0. For the change, so of course for A, it's easy because we have derived it already. So we have that negative Na0x. So that's negative because A is consumed in the process. As for B, C, and D, we have to be mindful about the appropriate term to write to account for that change, or the amount of moles of B that is reacted. Since our basis for the change, or our basis for the amounts of reactants that are consumed and products that are generated, is based on species A, so it's very vital to base the change terms for B, C, and D with respect to this term. Knowing the fact that this term that I boxed here in red is moles of A reacted, we should ask ourselves, how can I account for the moles of B reacted based on this term? Okay, so the stoichiometry, or at this point, the stoichiometry between A and B will come out. So of course, this is basic chemistry, and then what you're just going to do is convert the moles of A reacted into moles of B reacted by just using this term. And we need to have a multiplier wherein we have a probably a mole-to-mole interconversion between A and B. And what's the multiplier that we should multiply to negative Na0x to account for the moles of B reacted? So if you go back to the chemical equation, you have here B over A. So recall that B over A, this means that for every amount of B reacted, there is this certain amount of A that is reacted as well. So basically, for every B reacted, over there's also a certain value of A that is reacted as well. So if we're going to write that here, so I suppose writing this right away won't make you confused with respect to the the cancellation of units. So for example, what I meant was I will be writing a just a draft just to demonstrate what I meant. For example, if you have B, the B is moles of B reacted, because that's the, like, that's what the coefficients mean in a chemical equation, right? And then A is moles of A reacted. So that's the ratio of B over A. That's the unit. And then your Na0x, it's moles of A reacted. So if you notice, if you multiply the two terms, this moles of A reacted term will be cancelled out. So leaving you with the unit that is moles of B reacted. Okay? So that's how um, the change or the amount of B reacted is accounted for based on the product Na0x. For C and D, since both of them are sorry, since both of them are products, so they should have a positive sign because they are generated along the way, along the process. So you have to use the ratios C over A multiplied by Na0 x, and then also positive D over A, that is Na0 x. So all of them are based on the amounts of A that is reacted. So that will be easier. All right. So now, if you want to know the final value, you just subtract the initial and the change to get the final value. So you now have the following equations for batch systems. Final value, final amount. So we have here Na, which is equal to the initial minus change. Oops. That is Na0 minus Na0x. So that's how you write it. Okay. And then, oops, I'm kind of conscious as to how I properly organize my handwriting. And for NBO, I mean for NB, the final amount of the moles of B present in a batch reactor. So we have here NB0, it's not O, it's 0. Okay. B over A, and then Na0 x. And then for NC, it's equal to NC0 minus, oh no, it's plus because it's produced, CaNa0. So technically, you're not really subtracting them. You're just, adding them, initial and the change. And it just so happened that the change for the reactants are negative. So it's like subtracting the initial with respect to the change. But for the products, I think you need to add the change term, not subtract. Alright, so you have here Na0x. Alright, so that's it for your stoichiometry. Let's try to zoom out. Okay. So assuming, or if ever we are required to account for the total initial and the total final, so we can do it in this manner. So if we have the total amounts or the total species present in the batch reactor initially, so if we add, oh, I forgot to include the inerts. So let's add the inerts. You will encounter inerts soon when we deal with gaseous reactions, because with respect to how many moles are produced in a gaseous reaction, actually inerts actually do matter because they occupy space and they will affect the final or the equilibrium compositions in if ever you encounter a reversible gaseous reaction. But it's too far to talk about that for the meantime. So let's just focus on, just deriving everything. So with the inerts and then your Ni final, which is equal to the Ni initial, assuming that inerts, of course, inerts, they do not join or participate. So if we're going to add all of these values, so the total, okay, we can use a symbol of NT0 to signify or to indicate the total number of moles. That includes the inerts, okay? And also for the total number of moles at the final time, so if we're going to add that one, notice that okay, I'll just use green. In the first term, if you're going to add everything, I mean, it's Na plus Nb plus Nc plus Nd plus Ni, right? But if you are going to re-express everything according to its actual formula or actual equation, notice that the first terms, they are just actually a summation of the total amounts initially, correct? Notice? I hope you noticed that one. Okay, that's just NT0. And what would make the final amount or the final total amount vary is the fact that there are additional terms already. So this is the final total amount. And what will matter now is the second, or are these second terms. Okay. So if we're going to add all of them, so let's try to write all of them to really see everything. So we have here negative NA 0x, negative B over A, oops, negative B over A, NA 0x, positive C over A, NA 0x, and that includes, I'll just write it here, positive D over A, NA 0x. So notice that these terms that are written in red color have a similar term, which is Na0x. And of course, to make or to shorten our total number of moles equation, we can just extract these terms. So we have NT0, okay, and then we can extract all of them. I might do plus Na0x, and then so we have here negative 1 minus B over A plus C over A plus D over A. Alright. So we can actually rewrite this one to make it more beautiful looking. So we have here NT0 plus, okay, let's write all the positive coefficients first. C over A, D over A, minus B over A plus, oh sorry, minus 1. And then Na0x. So as you can see, we have here a special term which actually accounts for the total change in the number of moles of the system with respect to the moles of A. So it's like the, yeah, it's a ratio of how much or how many moles of X changed after the reaction, and that's with respect to A because all of them are divided with respect to A. So we can use a symbol called delta to account for this proportion. So we have here delta equals C over A plus D over A minus B over A minus 1. And then we can rewrite the entire thing. So we have here NT is equal to NT0 plus delta NA 0x. Alright. So that's it for the final total number of moles after the chemical reaction. Okay, for a batch reactor system. So what terms are important here? I think we should focus more on these terms. Okay, so that you will be knowledgeable in terms of deriving from scratch, because it would be very unwise for you to just accept equations as they are without really knowing where they come from. So in essence, we will not be actually using these four final amount equations, but we are going to use these equations to get into a more usable form, which is functions or probably concentration terms. Okay, so not any more number of mole terms, but we're going to determine the mathematical equations for the stoichiometry between the concentration of a certain component with respect to the conversion of the limiting reactant or the conversion of A. So for the next video, I will be deriving or making use of these four terms or four equations to derive concentration or to derive equations for batch systems with respect to concentrations. All right, so that's the part one. So we have here batch system with respect to n. So I hope you learned something from my video, and I hope to see you in my other videos. Bye.